Thank you for joining us for this 7th edition of Financial Security Conclave. And as we, every time, most of the DSCI event, we dwell into taking up something which is out of box, offbeat kind of a subject, right? And although quantum technology is not really new, most of us have been now getting ready for it, trying to understand it. So what I'm trying to not dwelling too much. So when we talk about quantum, coming from cybersecurity, we always talk about quantum security or cryptography. But here today we'll be dwelling on can we really build, and is the quantum technology especially, can create this trillion-dollar industry, and that's what people have been talking about. Last 2-3 years had been increasing realization of quantum technologies are coming. Last 2-3 years had been also very significant in terms of how the accelerations of this technology is happening. Last 2-3 years, especially last 6 months, had been also telling us that there is possibility of a utility-grade quantum computing. So this term I'm talking about, utility-grade quantum computing, is probably near to us. And there are a lot of ways, paths, and modalities basically which seems to be going to tell us that probably the quantum technology in various different sense basically coming to us. And this ecosystem that we talk about, until now it's more research ecosystem, but it's increasingly becoming industry ecosystem basically, right? So what this about, right? What that makes, why this industry is quantum trillion-dollar industry. But before that, we would talk about what DSCI had been in quantum. We had been following, engaging, dwelling into this area since 2015, working on some report that we did with DST in 2015 about the quantum technology. At that time, we were talking about this could happen in 10 years of time, and it's actually happening. To the area that we dwell into in terms of accelerating technologies in quantum technology, engaging with government on various different policy issues of quantum technology. Recently, we published a report in partnership with guidance with the NITI Aayog on a national security implication of quantum technology. We recently initiated the quantum technology and security training programs as well of Data Security Council of India. And you'll get to see tomorrow we have entire one full day of a special dwelling into quantum technology tomorrow. So there are a lot of things that the DSA had been doing in last 10 years of time in quantum technology, and all that really makes us to think about what is happening right now and what is going to happen from now. As a partner with the NITI Aayog on front-end technology, especially from national security perspective, we have been dwelling this subject quite keenly, and that's the report that we published with the NITI Aayog, National Security Implication of Quantum Technology. And then we started this. So before anybody has any idea about what will make this quantum technology trillion-dollar industry? Anybody has any thinking about this? Anybody? So that's always we talk about coming from security. But quantum is much beyond encryption and security, right? What will make the quantum technology? Which we'll talk about in short a while. But one is certainly encryption that we always talk about. Any other area why this industry will become quantum trillion-dollar industry? Anybody has anything? Yes, it will change the healthcare a lot, and there are various different applications of quantum technology, which probably new computing will create new possibilities in healthcare. And not only healthcare, there are many other areas basically, right, which will change the way the quantum technology will work. Defense is another important area. There already people are talking about 6th generation, 5th generation fighter pilot, which will have a lot of quantum technology, including a lot of those military weapons probably will be enabled and empowered by the quantum technologies, right? So climate is another one, the financial sector is another one, the energy sector is another one, transport sector is another one. So this technology, and we'll see why this technology will change these sectors, why it will bring those kind of revelations that we would see from now. And already there are a lot of quantum technology applications that we see as of now, right? So just a little bit about this training and certification program we launched some time back, and we are getting kind of good traction, which covers the technology and security, both of the aspects, and largely dwelling into technology area, largely dealing with the use area, largely dealing with the sectors that will get transformed because of the quantum technology, right? And with this background, let's dwell into what means the quantum technology. So what it makes the quantum technology. So there are three domains, primary domains of quantum technology, right? So one is the mechanics. So you want to use, work, leverage the quantum mechanics, right? And some of you must be knowing about this mechanics, superimposition, quantum entanglement, basically, for that matter, the Q measurement, or for that matter, wave function collapse. So many such mechanisms, which is a very weird science, right? We all know that quantum mechanics doesn't really have this local reality that we had been knowing about, right? I mean, there's a lot of weirdness there, but there are a lot of mathematical, scientific foundations for those weirdness, basically, right? And how you leverage, how do you make use of the quantum technology is one set of things that people have been looking at. For that, you may not require quantum computing computers, basically, right? Second important part is the processing. The kind of effort that has been going to harness the quantum state to process the information, to store the information, and to share the information as well, right? And this processing basically has been tremendous amount of effort and tremendous amount of the innovations are happening, and multiple modes of developing quantum technology out of photonics, out of superconducting, out of so many different areas, basically, people have been looking at, basically. And the third important part is the materials. So quantum would also bring a lot of those new possibilities for the material science perspective, right? So largely, when we talk about quantum technology, we are talking about the mechanics, processing, and materials, basically, right? And you're leveraging this capability for various different things, basically, right? So now let's look at what this means, right, for the industry. So there is when we talk about quantum trillion-dollar industry, so there is a quantum industry itself, processing, supply chain that goes for the processing, all the software, hardware, algorithmic, basically, element that you will be required to bring to this reality to the world, basically. So that's one important thing of the quantum industry, right? Second is the spin-off effect. Because of this industry, there are a lot of new areas that will emerge out of this, basically, right? Because of the quantum technology, there will be also interesting supply chain, because we know that when we had been working with existing ecosystem, we know that there are a lot of supply chain component that creates those data centers, that creates those processors, that creates those devices, basically, right? So quantum technology would bring new paradigm, and because of that new paradigm, new supply chain would get evolved, basically. So we all know GS is one of the important lens player, basically, optics player, basically, right? We all use it in our, mostly our specs are, we use the GS lens many times, basically. But now, because of their optical capability, they are becoming increasingly relevant to the quantum technology. Because some of the areas of their work is important here. Somebody working in a cryogenic is becoming important for the quantum technology. Somebody working in a laser is becoming important for the quantum technology, basically. So third important part of this industry is the supply chain that goes in terms of building the quantum technology, right? Then there are tremendous amount of competition. You must have seen IBM is working, Google is working, Microsoft is working, there's a Psi Quantum, there is Quantinuum, there is Rigetti competing. So we are seeing a lot of industries are now trying to get together to make sure this reality comes into the picture, basically, right? And because of this competition, because of the competition also getting quite a significant investment, we will see significant amount of the development that is happening and acceleration that will happen in this area, right? Another important part is the defense, as Dr. Devesh talked about. So defense has a significant kind of a relevance to this technology. You'll have a lot of applications, a lot of areas, be it Air Force, be it Navy, be it Army. Each of them would leverage the quantum technology, and they're already making plans for leveraging quantum technology, basically. Another important part is the research which is going, and this is a core capability that people are building. People still away from getting those utility-grade quantum computer, and people have been trying to find that. Microsoft is looking at topological qubit, Psi Quantum is on photonic computer, supercomputing is largely Google and IBM, and so many such kind of players are trying to do those fundamental research so that it enables, and there are a lot of foundational research happening at university, and at the same time, big players are also doing research in quantum technologies, right? Another important part is the different discoveries, and last 6 months and 7 months, we have seen a lot of breakthroughs happen. Google talked about it, Microsoft talked about it, Quantum talked about it, basically, right? And then we are also seeing the geopolitics also hitting bit quite significantly. Now people are increasingly, this is a next generation technology, and there are now effort to control these technologies as well, right? And then we are also seeing the investments, which is now, until now, government, but now increasingly the private investments are going lot in significant form in the quantum technology, right? And then we finally see is because of quantum capabilities coming in, because of these technologies coming in, we are now thinking about new applications. Until now, we have not even thought about the application that we'll think about because quantum capability is available to us. There is something called as a problem of a local optima and global optima. There are a lot of problems we are not even able to think because we don't have the capabilities available. But quantum will bring those capabilities to us in such a way that we'll start thinking those problems, basically. Thinking about those capabilities as well, right? And we'll talk about what kind of those problems are there, right? So these areas are contributing a lot to the quantum technologies and boosting the overall ecosystem of quantum technology quite intensely, right? So let's try to understand what this ecosystem means, right? So this ecosystem means one is the effort that is going to build the quantum computing, and it could be superconducting, it could be ion trap, it could be photonic computing, it could be spin computing, the different types of the qubits. And I don't want to go detail, but in quantum you talk about qubits basically, right? So rather than bits, you talk about qubits. So there are different ways to harness quantum states, and from that develop the qubit system or computing system basically, right? Second part is the circuitry we build on top of it. As you have seen in semiconductor ecosystem, here also you build circuitry on top of it basically, right? You also build a kind of a circuitry components as well, and there is a logical gates, different kind of a circuitry that you build, and there are effort that are going together to make use of this capability better, right? Then comes the hardware that people are making. Then comes the materials that are going into quantum technologies basically. Then comes the simulators that people are building to make use of the quantum, or sometimes your quantum computer is not available, but if you have a simulator, you can start thinking the behavior of the quantum computer basically, right? And you can also build simulators based on the quantum technologies as well, right? Then there is a control unit that you need, because you need to deal with the quantum state. So people are building control unit, and then people are also, the key part here is measuring the quantum state. That's why measurement equipment becomes very important. So all of these becomes a quantum technology ecosystem, or different areas and components and groups of the things that goes into quantum technologies basically, right? So this is a chip. This is just one version of a superconducting chip basically. So it has various different of this quantum, if at all you look at what Google talked about or IBM chip talks about. So these are the areas. One is the cryogenic equipment you need, superconducting circuitry assembly you need. You need to then create a quantum processing assembly basically. You need to have the measurement system. You need to have the control system. You need to have the entire qubits. There are different thousands of qubits, sometimes millions of qubits coming together. So you need to create a system to get an array of these qubits basically. And this arrangement needs to be engaged with an external ecosystem to FPGA semiconductor ecosystem, where our world, we could deal with the quantum world through this kind of FPGA controller system basically, right? This is a typical quantum chip, and for every type of the qubit, photonic it will be different, ion qubit will be different basically. This is largely for the superconducting qubit, where you go to cryogenic state, you go down the temperature, and that 10 millikelvin temperature basically, you try to achieve the superconducting environment, and then you bring a particular state to quantum state, and you harness that basically. And then you do many other things to make sure that you harness and you work and process the algorithm basically, right? So after the chip, basically, we also need to understand why this is becoming now reality. One is different components we looked at some different kind of chips, but if I have to really talk about quantum technology ecosystem, so these are the things basically. One is the hardware control and firmware system. People are building middleware. We need to build entire, I think this is an entire bottom-up thinking, bottom-up approach and effort basically to build the quantum technologies. What we have seen from 1950s to until now in semiconductor, that is similarly happening in quantum technology. One is the hardware and middleware, firmware, then middleware and compiler, then people are building programs and simulators, and at the end of the day, some people are trying to bring it for you to use basically, right? So in the hardware and middleware basically, so there is the control electronics, signal generation, the low-level drivers for that matter, the pulse-level programming interfaces for that matter, error correction and feedback for that matter, and very calibration environmental control ecosystem. See, quantum is a physical phenomena, right? And it does introduce some error. So you need to have some ways to manage and correct those errors basically. So it's one of the significant part of it basically, right? But quantum state, for example, one of the important behavior of the quantum, we all know that if you see the thing, it changes the state basically. It could be 0 or 1. If you are throwing the dice for that matter or throwing the coin for that matter, until you catch it, you're not able to see the value. So catching is actually interrupting. Interrupting is the seeing. So there are pulse, microwave pulse basically, they play that role. So with that pulse, you are able to see the quantum state and also modulate the behavior of the quantum state basically. So in our technology course that I talked about, we go down details of what that means basically, right? Then there are a lot of loud drivers that people are building for the quantum technology, and there are a lot of signal ecosystem which is going to help you to bring quantum computing out of this basically, right? Then there are organizations which are building the hardware abstractions layer. They are building quantum compilers and optimizers. They are trying to create a middleware hardware so that you can integrate their systems with other systems. We are also seeing a lot of programming language and SDKs in our lab. For that matter, we have built a quantum simulator in the lab in Delhi basically, right? Where we have used some of those programming SDKs available, and with that you can build quantum simulators and you can make some of the algorithms to work there basically, right? And then quantum error correction, calibration. So some of the software, middleware ecosystem, programming ecosystem is also now changing, and there are a lot of ecosystem players which are coming in this area. And as I rightly talked about, is the ecosystem is now increasing industrial nature. Until now it was more research, but now it's more industrial in nature. And at the end of the day, people are now trying to develop the applications. So you can make use of the applications basically. For example, some set of applications are quantum annihilators for that matter, specialized framework, which you can use to do simulation algorithms. You can use to run the quantum algorithms specifically. There are machine learning integration with quantum technology. There are user interface and experiment that is going on. Some people are building all of that in quantum technology. IBM Bracket service, if you look at, it's bringing a lot of quantum computer available globally, and you can make use of that using the Bracket service basically, right? So many of such kind of capabilities that are now getting built and that are getting make it available to you. Either you can buy quantum computer, it's cost a lot nowadays, or you can access quantum computer over the cloud as well. So a lot of cloud providers which have been bringing those capabilities as well, right? So this ecosystem, once you understand this ecosystem, once you know different components going in this ecosystem, then you start understanding why the people who are building this are now getting significant traction and investment in the overall market ecosystem basically, right? So if you have to really talk about the people who are building all that. So level 1, specialized material you require for quantum technology, quantum electronics that is in play, cryogenic system that people are building, some fabrication tool. Now you need different fabrication for quantum chip basically, right? And you need to have those players. I had myself seen, when I visited last month to US, I had seen one quantum foundry there basically, right? People are building foundry for quantum technologies basically. There are a lot of efforts being put together for creating specialized vapor for the quantum technologies basically, right? Level 2 is something that people are building the quantum computing, and mostly we know of, for example, IBM, Google, or quantum machines players like a Psi Quantum or AGT computers. So there are a lot of players in the market now, hundreds of players now, which are trying to build the quantum technology or quantum processor basically, right? And from this, I think there are a lot of these quantum computing infrastructure ecosystem where people are building those kind of algorithms, those kind of middleware, those kind of programming language, those kind of SDK frameworks basically which can make use of it. And at the end of the day, there are programming tools available to you with IBM, Google, you can use it, and based on that, you can at least start working, start using, start experimenting with it actually. So this ecosystem is going to become a significant ecosystem from now, right? I know largely as a security community, we always had talked about quantum creating threat or quantum breaking the encryption basically. But getting a little bit understanding about what this ecosystem is, what exactly the quantum technology is coming in, right? What kind of efforts which is being put together, right? So that will help us understand how exactly this will change. This will bring new paradigm altogether for computing environment basically, right? So let's try to understand this timeline, right? That's what people talk about. So what is going to happen from now to next 10 years of time, and this timeline, this is the effort that we put as a Frontier Tech initiative with working with Niti Aayog. So we are currently at early stage of the quantum commercial phase. We are using this, we are into NISQF. It's a noisy computer ecosystem that we are into basically. And there are a lot of commercial applications which are already there and people are using this for different kind of applications basically, right? We have 100 plus qubit system. We also have version 1 of quantum center. Some of the defense applications have been using it. We are doing basic level of error corrections and now it is going certainly to the next level, and by end of this year, IBM already talks about they probably will bring 1000 qubit computer computing ecosystem. But they're saying by 100 to 300 qubit, that machine will be so powerful. It will start doing so many different things basically, right? And we know even by 25 qubit quantum machine, we can break AES 32-bit encryption basically, right? And more, although this ratio is exponential. So for breaking AES 256 for that matter, or RSA for that matter, we probably need 1 million qubit quantum computer. But can you really bring that in early space? So that's what the timeline talks about, right? So once starting next year, probably we'll see a lot of acceleration coming in the technology, right? So we'll see 1000 plus qubit system, we'll see the quantum memory, quantum internet pilots, a lot of advances will come into picture. We'll see 2030 to 32 is mostly the integration phase. People in various different lives will start using quantum capabilities for different kind of applications basically, right? And then we'll probably see 10 years or 7-8 years from the now, probably you'll see the very mature million qubit system. And DARPA, some of you must be knowing, is one of the research institutions of a defense research institution. So they have selected, they use the term called utility grade quantum computer. That means the quantum computer, you can use it for day-to-day critical purposes basically, right? And they have selected a couple of players which can make that 1 million qubit possibility, right? And they are saying that next 7-8 years of time, things could really bring to that level to us basically. We would have utility grade quantum computers. There is another term which is used, the cryptography related quantum computer, QRQC. Means the quantum computer which is relevant to the cryptography, which will be able to break the crypto basically. So that's the capable quantum computer will be coming in probably next 5 years, 6 years down the line, and now increasing new innovation happening, new breakthroughs happening basically. That tells us that probably this timeline is getting increasingly accelerated actually, right? So the timeline is possible because of so many different innovations are happening. Materials, hardware, control systems, software infrastructure. All of these are making this timeline to get more and more acceleration, more and more investments coming in, right? So this timeline, through this ecosystem, if you try to now look at what will this mean to, right? What kind of problem it will solve, right? So the problem that we know right now use, a problem that we right now solve, right? And these problems are largely the thinking of areas or ideas of problem basically. There is some concept called as a local optima. There's some concept called a global optima for that matter. We know in financial, I take an investment product for that matter basically, right? We know that a lot of things happen globally at this point in time, a real-time basis, and which has a lot of impact on the returns that you get on an investment you made basically, right? Currently, we don't have the mechanism which can process the data to that level of significance, basically, to that level of speed. One is the complex speed, another is the multi-dimensional data, basically, to take the decision, basically, to take the decision real-time basis, basically, right? So many problems, and that's why, because we don't have the capability, that's why we use a lot of these local variables, local parameters, only local thinking to solve the problem. It's called as local optima. But once we start getting this capability, once we start getting quantum kind of capability, which can process data at a level, and you know, Google talks about they could able to process data in a 5 minutes time, which would existing ecosystem or existing computing system would have taken some 100 millions of years to process, basically. So that level of processing difference we are talking about. So when that comes in, basically, then we'll start relating our problems to the global variables, basically. We'll start then putting together a lot of these kind of ideas. In those ideas, basically, we'll start seeing that probably this problem I need to process this much of data from various different dimensions, basically. And with quantum, suddenly you will become organization, and that's why one of the important things that we had been talking about is whatever is available, if you don't use it, whatever capability of quantum computing, be it 25 qubit is mostly available, 84 qubit is available, 100 qubit is available for that matter. If you don't use it, you not know how to use the capability for the next generation solutions that you want to do, or new generation idea that you want to do, basically, right? So in US, I'm seeing a lot of financial institutions for that matter, a lot of defense organizations for that matter, have been actively using what is available right now, actively using what are capability available right now, basically. And once you start using it, you'll know how to use it for various different kind of use cases. By using, you'll also try to find new ideas as well, basically, right? So the problem of the current age and the problem of the future age, basically, in the world which is very integrated, very interdependent, very complex, basically, right? And something happens somewhere could impact what is happening here. In this very complex, interconnected geopolitical situation, if you are not able to bring all those kind of global thinking, so saying is easy, but there is some instrument and tool for you to have that global thinking variable and data to process in a real-time basis, to take the decisions for that matter. I mean, we are talking already there has been experimentation about quantum could replace the GPS and quantum radar for that matter. And many of the defense organizations are looking for that, basically. Without GPS, can you really map the topology, basically, on a real-time basis, basically, right? Without any such kind of a support of existing technology, can you really do many things that you want to do in a military ecosystem, basically, right? So all of those possibilities will now get open once these capabilities are available, and use of these capabilities that becomes very important part, basically, right? So this is one part of the story, basically, one part of the discussion, right, in terms of understanding this technology, right? Any question or doubt so that I can go to the next level? Yeah.
So very interesting. One thing is there are certain branches of maths like chaos theory, which essentially said that certain branches of maths like chaos theory, which essentially had saying that a butterfly flapping its wing in China can cause a flood or a climate change in Brazil or something, was possibly due to the fact that they could not crunch so many variables at a time in order to judge the outcomes, various different outcomes that are possible, or even for a human mind to comprehend how many outcomes are possible. Will such branches also undergo major changes by bringing chaos, by bringing quantum solving?
Yeah, so one of the application, health, somebody talked about health sector, right? One of the application is right now the MRIs and the scans that we have at a very, very tacit higher level, basically. So now there is there is even, people are saying that you could able to now scan even cell and cell temperature, individual cell and cell temperature level basically. So we say that body is a Brahma, right? It's such a complex body. If you understand universe, you will understand body. But there was no technology available for us to understand our body, each cell and its behavior. But now the quantum would help you not only understand but know scientifically much better basically. If that is possible, there are big problems like, for example, currently the big problem is the climate, and one is problem, but second is meteorology, understanding or estimating what could happen, to the extent of pollution, to the extent of traffic management, to the extent of the power generation and distribution optimization, grid optimization for that matter. Many such problems that we had been thinking about, we didn't have much of the competent capability available with us. Now, these capabilities can help you. One is multitude of data, one is the speed and multitude of data and complexity of data, and processing that in a such a way that it's a fractions of second processing basically. Right? So a lot of these possibilities it will enable, and that's why the quantum, there is a Grover's algorithm for the matter, quantum's Grover algorithm, which can search a particular thing out of the trillion sets of data basically for that matter. So there is a Chinese one research recently happened, they could able to create billion different parameters and trying to find, using quantum technology basically, trying to find solutions out of that basically. So a lot of these capabilities would now make you think about those problems you have not even thought about. We recently worked with one of the state and talked about the different kind of the use cases where state can use it. So grid, definitely optimization of the grid is a big challenge, and can you use this? Especially the future grid, which will have a lot of two-directional thing. People will be generating, sharing, every equipment or every device is electric in nature basically. You will drawing power. You are also supporting, because you will be also generating as a part of that, you are also giving power back to the grid basically. In this complex ecosystem, how can you optimize the grid basically, right? How can you make sure the agricultural development, for that matter, there's tremendous of the dimensions. There is a dimensionality curse that we talk about. So currently we are not able to think of all the dimensions, and that's why we are not able to process it, and because of that they are not able to solve the problem basically. So there are a lot of those ideas which can come out of the quantum technologies basically. Yeah.
Dr. Dinesh here. The major challenge which the development of quantum has been experiencing for quite some time is the dilution, refrigeration, and maintaining those temperatures. I mean, I'm referring to the cryogenic this thing, which is essential for stability of the qubits. And if that doesn't take, if the stability is not near perfect, then you have the error problems which are there. Since you've been to US and you mentioned about DARPA, in fact, DARPA was also looking at it as a huge challenge, because in defense application, a minor error which takes place during processing of any algorithm, which it will amplify to something which will not make it suitable for defense application. So if you can throw some light on that as to where have we reached.
So question, what he is asking, at the end of this is a physical phenomena. Because you need to bring material to the quantum state, and that quantum state can be done either through cryogenic. I talked about, you bring down the temperature to the level where you bring that particular superconducting matter to quantum state, and then you build a physical qubit. So the concept of physical qubit and logical qubit. So multiple physical qubit, because there are error, because there is a noise, simple noise. In fact, there is a, you can't build quantum superconducting facility more than one floor. More you go to the next floor, there is a small noise will disturb it. Mostly is ground floor or first floor. That's the standard for that, right? And because of small noise, it may disrupt, because at the end of the day, it's a seeing, it's a physical activity basically, right? And there is a noise that happens at a physical level, and there are ways that you cover at a logical level. So you can manage that noise at a software level basically. And there are surface code, and now IBM talked about new code they found. So there are a lot of organizations which are trying to find, we manage those errors at a software level. So means what will happen, ki out of 1,000, you will create one logical qubit. 1,000 physical qubits will be required, and you have one logical pure qubit basically, right? And that's why they are saying that they will need 1 million physical qubit to have the sufficient amount of the logical qubit to process that information or break the encryption for that matter basically, right? So at a foundation level, be it a photonic, be it superconducting, there is this challenge of scaling that. Challenge of scaling to the level, to bring that to the level of utility grade quantum computer basically, right? But then people are saying that there are 2-3 ways to think about it. One, I'll talk about that. One is what will bring the 1 million qubit, and we'll talk about methods about that. And secondly, can you do hybrid ecosystem? You use some part with quantum and some part with quantum computer basically, right? So some company like Regit and all, they are looking more hybrid solution. But some companies like, for example, topological qubit of Microsoft, it talks about way that topological qubit, we do sessions, detailed session topological qubit basically, where you make that qubit using nanowire in such a way that inherently stable. There is inherent stability now people are talking about, and that's why DARPA selected Microsoft as one organization who can realize the goal of a utility grade quantum computer. There's another which is PsiQuantum, which is a photonic computer. Photonic computer is good because we already know a lot on photon, because we had been using for communication. Now recently we have started using for the processing as well, right? In photonic, PsiQuantum is trying to do, they will make that one qubit so error free. And once they make one qubit which is equal to one physical is equal to one logical qubit. So that's the equation they're trying to it. Then they can have modular way, 1 million such physical qubit talking to each other, and that's why it will bring 1 million qubit to photonic side. So there are foundational way which is happening at a physical level, and there are 2-3 candidates. Microsoft is one, and PsiQuantum is another. There are many other, for example, I run about dwelling into out of this spin qubit, untap qubit, which one is more stable basically. So stability matters a lot. There is a coherence time people talk about, which once you bring the material to the quantum state, then how much time you can maintain that quantum state without too much of the effort, right? So the refrigeration at that level, and dilation refrigeration for that matter, is one of the significant part of the supercomputing. But the other areas of photonic computing, photonica and all these things, so those areas are becoming very interesting in coming future basically. But there are a lot of science and development happening, and these are the problems that people are solving. And some of those problems get solved, suddenly you'll see this big jump coming in basically, right? I mean, Microsoft is able to now scale up. So they could able to build 8 qubit processing unit with this topological qubit. If they're able to scale up to 1 million, and their technology seems to be good because of the nanowire. There's already technology improved on that. The current foundries can make the millions nanowire in 1 or 2 centimeter kind of chip basically, right? If they're able to now scale that up, they will be able to bring the 1 million qubit quite early basically. So these are things that are evolving and that's why this space becomes so interesting and important, and somebody which is trying to think about new businesses for that matter. So this throws quite interesting kind of ideas and interesting kind of possibilities in quantum technologies. Yeah.
There's advanced sensors. Now that a lot of research is going on for these quantum satellites, for hiding your own signatures or cryptography. Any use case on which we can think of the stealth aspect? How much to show, how much to detect, and how this detection of materials can be done? Because you need to hide yourself. What all things have been
So
done?
one is the material, right? So quantum material can help you to build those materials which are stealthy in nature. So this technology can work you both. One is the bringing the stealthiness, and other part is even anti-stealthy technologies as well. There are 6, 7 technologies. I recently made a map of anti-stealthy technology, and quantum stands on the 3rd or 4th capable technology. There's quantum illumination as a concept. Means quantum illumination can make sure that existing stealthy technology, you can illuminate them and try to identify them basically, right? So both of side, quantum technology has answer to. One is it can help you invent a material which could be more stealthier than what we say until now. So the metamaterial for that matter. So quantum can really help you some of the different candidates of metamaterial. That's one part of the story. Secondly, quantum imaging can help you to eliminate those devices or those equipment which are not otherwise able to detect in other technology basically. Both of side, I think there are a lot of innovation happening in it.
Surface, something is hidden. You want to detect these things with the help of quantum technology, which is not detectable otherwise with open.
Yeah, so under
so those kind of
surface-
signature management.
So under surface is now, after what happened last 1 month's time, under surface detection, especially some of the very strategic asset and then finding signature of that and getting hold of that signature and try to identify. And so quantum technologies can help you understand that basically. In fact, now there is a very interesting research is even birds, especially those birds who travel for thousands of miles, they use quantum mechanics basically, right? So how do you understand that? And that's why in the evening's time, today evening, it's a very invite only. We are doing this session. I hope that we are doing that session, right? We were talking about this technology and how they will help you achieve some of the strategic military goals. So today, 7 o'clock, we are doing this session actually. We're talking about all of these things. You can take this and then I can go to next, yeah. Can somebody pass the mic, please, quickly?
Yeah, hi. So I have a basic question related to the quantum theories and everything. As you talk about the government and the military is heavily investing into the quantum safe technologies, right? What do you think if we talk about the scaling phase? Is it hard to scale? Will it be still expensive and it would replace all kind of encryption?
Yeah, so this is a certainly question. If some students in their 7th, 8th grade talks to me about AI, I get scared. They should be try to learn the new computing which is coming in. Somehow it's not coming to that level where next generation, in fact this generation as well, those who are studying engineering. So recently somebody met me who is doing, working with one of the semiconductor company and doing this chip design. So getting people to see quantum technology, making them understand this quantum mechanics, processing and material is one part, but it's not only quantum. So there's a hybrid computing environment we'll see. Quantum is one, but neuromorphic computing is also coming. There's a photonic computing also coming. DNA computing also coming. So suddenly you'll have 5 to 6 different type of computing basically. And getting students and especially next generation to engage on this is very important. It's not easy. It's very scientific and very mathematical in nature. But there's also industry. That's why we started our quantum technology program basically, so that we create an industry capability to understand this better basically, right? It's not easy area, but there's not much awareness about it as well actually, right? So with these questions, let me go to the next level. So we talked about this local optima and global optima, and this problem I can talk about in terms of the cyber security, right? And this is very interesting for cyber security. So we know until now, when there is not much interdependency, not much complexity, we have been solving problems of cybersecurity with some regulations, some control framework, some compliance requirement basically, right? And then we realized that when things are very interdependent, not very complex, we can solve that by designing this much better, putting good protocol, and then probably connecting, doing this design thinking much better, basically. And now when things are very complex in nature, we started using automation and AI can help you better, basically. But when things are very complex, very complex and very interdependent, basically, you need a lot of those systems thinking. You need a lot of those kind of small minutest element needs to be factored to solve the problem, basically, right? And when you have to, and that's what the problems of security now coming into, right? So finding that one problem out of so many different possibilities, basically, is a big challenge, right? And we are increasingly coming into the level where we usually talk about there is a complex challenge, but there is underneath those challenges, basically, a lot of resource constraint, lot of those uncertainty, lot of emerging partner, lot of hidden factors, basically. So getting hold of it, basically. Getting hold of all of those complexities, getting hold of all of those kind of dimensions, getting hold of all of those kind of contexts, all of those kind of content possibility, right? And that to doing in a very real-time basis, basically. So this capability, and there are some companies I know of, they are trying to see quantum simulation, quantum optimization. They can use it to understand the security better and take the decisions better, basically, right? So security definitely is one of the important candidate to see probably problem statement area, basically, that can really leverage the quantum technology much better. This is one example of it, but there are multiple applications. One is so I try to create a map to understand different areas. One is the information technology, and we know complex problem exponential faster. Currently, we have 100 to 1,000 qubit, but eventually we'll go to a million qubits for practical application that will be required. And these problems, and each of where we are trying to say that currently where it is, basically, right? If you take example of transportation, right? There is a high precision GPS-free navigation. And using quantum sensor is already in experimental stage, basically. And eventually people will be using it. Prototype exists, but still not really robust. But eventually it will become robust to use in practical commercial sense, basically, right? Third part is the quantum enhanced photovoltaics, basically, right? Where you can improve the solar efficiency. If that happens, basically, that will be revolutionary in terms of the energy that we consume, basically, right? There are still a lot of efficiency problem in a renewable energy that we look at, basically, right? So currently, there is a promise, quantum dot can help you in that, but commercial viability not yet proven fully, basically, right? Example of a quantum finance for that matter, the powerfully optimization this analysis using quantum simulation and optimization algorithms are available. Now increasingly it is becoming available. There are a couple of Indian startups help you do this, basically. Couple of our startup itself, DSCI Incubator startup itself, they help you doing this, basically, right? Chemistry and material science, I know there are some few people in India and this is the area where a lot of innovations would happen and a lot of those kind of military specific advanced material research would come in this area, where material with exotic property used for various different kind of energy and other requirements, basically, and simulation of molecular structures and reaction, which could help you to find new materials, new metamaterials as well. So that area, there's a lot of promise, and I know some people in India which are working on this area, and we know somebody like TCS has a practice in this quantum chemistry practice, basically. Medicinal biology, a lot of things. For example, quantum sensors for medical imaging, high precision MRI or NMR spectroscopy, widespread applications are years away. When we talk about this technology course we do dwell into quite detail in this quantum biology. How do we understand? So I was talking about understanding how the bird flies, understanding how the photosynthesis happens. If you understand that better using quantum technology, we're able to emulate that much better, basically. So currently people are debating whether it can be possible for that. And I believe environmental science, so in terms of detection of greenhouse gases and pollutant, and increasingly the quantum technology is making sense for this, basically, right? So these applications are larger, bigger possibility, and there are a lot of applications which are coming in the discussion. People are working on that. especially defense ecosystem is now pushing hard in terms of these applications a lot, basically. And a lot of investments are coming from defense side, but commercial applications. I'm seeing, I visited a couple of quantum technology companies, and I'm seeing the big companies, how they are investing to use it. Our big problem of this society is we are not using it early in the game, right? And that's why we miss on working on those kind of technology, right? So using it early in the game is very important. Unless you use it, then again it will happen like in 3-4 years down the line, we'll again start playing the catch-up game here. And I'm seeing that happening in quantum technology a lot, right? So, how does this could happen? I mean, they're saying probably by early 40s, quantum technology industry will probably reach to $1 trillion market share. And if this would get advanced, if the first commercial grade quantum technology comes into picture, this timeline may get advanced basically, right? And there are serious possibility that we would see this ecosystem growing in such a way, the investment, the technology ecosystem, the research, the investment happening in such a way that, so this possibility of $1 trillion market value by early 40s is possible basically. Because suddenly there is a exponential growth in terms of use of this technology that we'll see in some past basically, right? So this $1 trillion industry, how can we make a relevance to this as a country, right? One is the adoption, use and adoption, which is very important. And I see some geographies, China and US for that matter, they're very aggressive to adopt this in defense ecosystem, in a commercial application, in financial sector, in health sector, energy sector for that matter. So enterprise adoption is critical for this market, right? Second part is the emerging applications, right? Means if you are able to find various different applications, that application itself will then you make use of this technology much better, basically, right? And then another important part is the transformational potential. As we have seen that because of this capability available in such a way, this could change various different sectors, including the health sector, energy sector, transport sector, right? And this could bring the different altogether way of doing in different kind of sectors basically, right? And definitely government initiative matters a lot, especially investment for building this ecosystem, but investment also to build the algorithms and applications, and more importantly, government initiatives to promote the use of this technology, basically, promote the use of this application of this technology. So they will matter, and that's what we are seeing. So one is the quantum mission that government of India has, but there is also Andhra Pradesh has recently talked about, or even for that matter, Telangana also talked about, they are becoming, they're aggressive in terms of becoming quantum state. So we are working with some of the state government to write their quantum strategy, basically, right? So more active you are, more active effort you are taking, and currently this is still not an expert control technology. Large part of it is still not into the expert control list basically. So what we are trying to see, can we bring those capability much early in the game so that we can start using actively in the country basically, in defense ecosystem as well. I know when we talk about quantum, we always talk about cryptography, but we are saying that it's not only cryptography. Just imagine you're using it for quantum radar. Just imagine you're using it for optimization. Just imagine you're using it for various kind of technologies, for the stealthy air technology, for eliminating the stealthy material for that matter, right? And we are worried. So J-35, if suppose that comes from China to Pakistan, which is a stealthy aircraft basically. So what is our defense against that, right? So we need to find ways to adopt and use it aggressively, and that could something government can enable apart from the enterprises doing this, right? So these are some of the challenges on a quantum computing advancement. So one set of challenges definitely technology maturity, as Colonel Dinesh talked about. Still in the maturity curve, currently still very noisy, but day by day it is improving a lot. So there's still a scalability issues, there's still stability of the qubit is an issue, and there are a lot of efforts that should be taken for the error correction. That's the area that most of the effort is being put together. That's one set of the problem. Second is the infrastructure ecosystem. Although that is improving a lot because of the private players' investments coming in, but then you need a lot of different ideas for hardware, software development for this ecosystem, because this is entirely from the scratch, new way and age of quantum development. So you need to build a lot of new middleware, hardware control system for that. And there are multiple modalities. We say this multi-horse game, basically, right? Superconducting, photonic, spin computing, ion trap for that matter, right? In that game, basically, we need to have multiple those development. And as somebody lightly talked about, skill shortage is definitely important area that needs to be looked at. And then algorithm development. If you don't use it, and if you don't understand the nuances of this classical method. So quantum method and classical method, they are two different things. Right? Classical is very local in nature, real and local. Quantum is global and a little bit weirdness, right? Quantum is the classical world is very real and very predictable. Quantum is very probabilistic and weird and global in nature, basically. So how do you make use of advantages of this capability? And then we also need to bring a lot of practicality into this algorithm, basically, right? How can you use Grover's algorithm for solving day-to-day problem, basically, right? So these are the efforts where we believe a lot of things being put together, and this will make this industry a reality. The efforts in this area goes well, and they progress the way we have been envisaging. Maybe in next 10, 15 years of time, quantum will become very significant industry. So this is my last slide. So yeah, no. Yeah, there are a lot of, the challenge here is this is still a very fast growing area, right? And that's why if you start putting standard early in the game, it's like putting grammar before language progress, right? But still there are effort. For the PQC we talked about, there's a standard that NIST wrote for PQC, something which can be used at a ground level, at a literal level, basically, right? So it's not easy, but at the same time, there are a lot of efforts, basically, right? Because, yeah, so standardization efforts are also in progress, but they will always follow to the innovation that comes in the picture, basically. Right? There's still too much of a acceleration happening in this area. There are areas where you want to practically use the standards will come, but this is a very probabilistic world that we are getting into. And AI is also telling us that, right? AI is very defined. Pre-area AI was very defined, predictable. Now it's more probabilistic in nature. So finding a standard for such world is not that easy game, basically. Right? Yeah. Yeah. Can you quickly circulate the mic? Here. See.
Hello, sir. Yeah. As we know that, we have very little time because as quantum is evolving, and practically, if we see, we'll have to start now of looking into the quantum migration. And my question to you is that is DSCI also involved in in research and development of the safer algorithms, like as NIST has done, like the Kyber.
Yes, we are involved. This today is not. We are doing tomorrow entire day on security service. That's what I want to break today. Quantum is not only cryptography, not only quantum security. Absolutely. Think beyond it, right? Tomorrow entire day we are doing a special full day on quantum edge as a session. So there you'll have a lot of discussion on quantum cryptography.
Absolutely.
But think beyond that. But that had limited us in last 3 years of time, 4 years of time, basically. So one last question, and with that we can close. Anybody? Oh, okay. You have a question? Oh, okay, sorry. Okay, then with this, I hope this was useful. And I think getting aware, getting beyond the orbit is very important, and understanding this entire ecosystem in totality, and knowing what is happening. So we say this is edge of current paradigm. So you should know what is there as a current paradigm. and what is the age of that current paradigm. And if you don't know this is the age of current paradigm, you're not to get to know what is happening after this basically. So next breakthrough will only able to get hold of it if we don't know the age of current paradigm basically. So the active effort to know the age of current paradigm is very important. This was the effort to bring that to the table. Thank you for joining, and we are starting the inauguration at 10:30, and I hand over to our MC here to take discussion forward. Thank you.